All right, welcome to our last topic for our lecture video series on Wednesday, May 3rd, where we bring up Dalton's law of partial pressures. So let's begin with a definition of what Dalton's law of partial pressures actually states. And despite it having a very lengthy name, it's actually conceptually something that makes quite a lot of sense. So let's think about this idea of a partial pressure. So if we're talking about a partial pressure, we're talking about a mixture of gases, right? Where we're considering the pressure of one gas compared against another. So Dalton's law of partial pressures states that pressure is summative. Now, what on earth does that mean? A mixture of gases has a total pressure that is equal to the sum of the pressures of the component gases. So for example, let's say that I have some kind of container and I fill it with some pressure of gas 1, some pressure of gas 2, and then some pressure of gas 3. So I'm like pressurizing a container. Then if I want to know the total pressure in the container, that's going to be the pressure contributed from gas 1 plus the pressure contributed from gas 2 plus the pressure contributed from gas 3. So for instance, if we think about like atmospheric pressure at sea level, remember the atmosphere is a blend of different gases, namely things like predominantly nitrogen at around, I think, 75-ish%, maybe a little higher. Nitrogen gas, then oxygen gas, followed by things like carbon dioxide, and then we've got argon, we've got then of course like methane, pollutants, SOXs, NOXs, things like that. And if we were to think about the atmospheric pressure at sea level, assuming that we're at some constant temperature, then the total atmospheric pressure is going to be due to the pressure contributed from the nitrogen, pressure contributed from the oxygen, pressure contributed from our argon, pressure contributed from our greenhouse gases, etc., etc., etc. That should all be equal to 1 atmosphere. So why is this useful for us to know? Like, it seems like we're kind of just stating like something that is obvious, right? That, oh, okay, yeah, if I've got some quantity of pressure, then if I'm just stacking pressures on top of one another, then the total pressure is their sum. So why is this something that's useful to know? This is something that we care about as chemists because let's consider, for example, a combustion reaction. So let's suppose that we're looking at the combustion of methane. So methane is CH4 plus oxygen, yielding CO2 gas and H2O gas. So let's figure out what is going on in this reaction. So let's say that we've got excess oxygen. So as this reaction happens, we know that our methane is going to be completely consumed. So I've got my reactants So let's say we've got methane. Okay, that is going to be an excess oxygen. And then that is going to form CO2 and H2O. Oop, that's an eraser. CO2. Okay, everything's 1 to 1, so I have to have the same amount of methane molecules as I do carbon dioxide made. So I had 1, 2, 3, 4, 5, 6. So I need to have 1, 2, nope, that's all used up. We need purple. 1, 2, 3, 4, 5, 6 moles of CO2 made. And then we've got our H2O gas, which again also is in 1 to 1. So I've got 6 moles of that made. And then if I count up how many moles of oxygen I had, I should have used up 6 to make these products. So I had 1, 2, 3, 4, 5, 6, 7, 8, 9. So I used up 6 of those 9, leaving behind 3 moles of CO2, or sorry, of oxygen left over. Let me make these just a little bit bigger so that you can count them perhaps a little bit easier. This is me just doing some like off the cuff stoichiometry, using what I know about my mole quantities and mole ratios of gases used here. So I use 1, 2, 3, 4, 5, 6 moles of methane and 9 moles of oxygen. That created 6 moles of CO2, 6 moles of H2O, and then the remaining 3 moles of O2 in our product vessel. So if I want to think about the total pressure of our reactants system, this is going to be the pressure of methane in that container plus the pressure of the oxygen quantity in that container. And then in my products, this is a mixture of now 3 gases. I have my product carbon dioxide gas. So the total pressure in that product vessel is the pressure of carbon dioxide plus the pressure of my water vapor plus the pressure of my leftover oxygen. Now, how these pressures changes and how we would find them, well, that's coming up. That's called gas stoichiometry. That means we got to use our ideal gas law as a means of getting moles. So stoichiometry doesn't go away. Remember, stoichiometry is looking at our mole ratios from our balanced chemical reaction and then using mole quantities gotten from a mass and molar mass or a volume and molarity to get moles. Now we're just adding for ourselves a new method of determining moles, which is the ideal gas law. Because remember, the ideal gas law, way up here. Oh, I could rearrange this to solve for moles. So we can relate moles to then pressure when we look at systems that have gaseous components in them in Chem 210. All right, I think I want to do... You know what, let's start with a warm-up on Friday where we look at how we can apply both the ideal gas law and Dalton's law of partial pressures. On Friday, May 5th, Cinco de Mayo. And then from there, we will do a little bit of gas stoichiometry. So we'll go back to kind of questions like this one or problems that are like this one, but we'll be given a lot more information so we can actually do some calculations and figure out some actual quantities. And then after that, we will introduce the idea of vapor pressure, which we'll probably continue talking about into early next week. And then that will wrap up our conversation of gases and allow us to move on to talking about liquids and solids. So I will see you on Friday, and I will see you tomorrow for our beginning of our Hess's Law lab. So have a great Wednesday. Thanks, folks.